Good evening, everybody. And today we are going to discuss a very interesting and very important concept in static electricity, where the charges never move. They are static. They are there at some surface. So today our topic is on Gauss law and its applications, how to apply this Gauss law and all. So let us, before going straight into the gas law, let us go through the fundamentals and we do some problems also today. So let us see. Yeah, I think you are looking at my notepad. Let us take, for example, we all know when a positive charge is there, yes, charge is there, the electric field lines will spread uniformly, normally in all directions like this. We know it, right? If whatever this electric field line is going, this effect we can see in this vicinity. How? See, if this electric field line is going away from the charge, here some medium will be there. So these field lines must go through this medium. So whatever the effect, this is the electric field direction. So from the positive charge, all the field lines normally spread in all 360 directions going away from the charge, positive charge. They are spreading away. So here, the effect of electric field we want to calculate, we have to know. Then before this electric field reach this place, it has to go through this medium. So if this medium allows this electric field line, then only this effect will be prominent at this place. So this medium has to allow this electric field line. This property of the medium which allows this electric field lines to it is called as permittivity. Permittivity. The symbol we use is epsilon. So if nothing is there, if air or vacuum is there, then the permittivity, we say no, we use the symbol epsilon naught. This is the permittivity. If air and medium is not there, some other medium is here, then the permittivity may be some other value. It is not epsilon naught. So symbol we use epsilon naught for the permittivity of the air and vacuum. If other medium is there other than air and vacuum, we have to use this epsilon like this. So if this electric field lines are coming out here, the more number of electric field lines comes here, we say at this area, electric flux is more. So how to calculate electric flux? Let us, for example, a positive charge is there and electric field line is there going normally in this direction straightly, and one surface is there here. This is the surface, the area small surface I have taken, so I named this surface as so S is the symbol we use for the surface, ds, surface, small surface. See, the surface is spreaded like this, so the direction of this surface is in this direction. This is the unit vector normal to this surface. So this vector, we call it as a aerial vector. This is always normal to the surface. This is the angle it makes. So if the electric flux we have to calculate in this area, so what is the formula we use for the electric flux? Electric flux is equal to the scalar sum of scalar product of the this electric field and the area normal to this area. So this is the aerial vector, we may say. So simply we write it is a small surface. So this is a small flux here at this surface, at this vicinity, at this area, at this place. So d phi is equal to, simply we may write ds bar. So the dot product we know, so ds cos theta. This is the flux at this surface. If the positive charge is here, the electric field line is here, and the surface is like this. So the surface normal, this is a small surface ds, the normal drawn to the surface is in this direction. So this is a unit vector normal to ds. So here the flux at this surface at this place is equal to the dot product of E bar dot ds bar, but we know that the angle between these two, this vector and this E bar vector, we call this vector as a aerial vector. The angle between aerial vector and electric field is 0. So E ds cos theta is the formula. Here you see this formula, where whenever we get trigonometric functions ratios in any formula, this total value, this one, becomes maximum when this trigonometric function becomes maximum, and minimum when this trigonometric function becomes minimum. So in this discussion, the flux here is equal to the angle between ds bar and E bar is equal to 0, cos 0 is equal to 1, so EDS. So from this discussion, the conclusion is, see, if an electric field line is going through a medium, it has to allow the electric field. So this property of a medium, we call it as a permittivity. If air and vacuum is there, permittivity value is epsilon naught. If other than air and vacuum is there, it is epsilon. But how to calculate the electric flux? Electric flux is what? The number of electric field lines passing normal to the surface. So I have taken a surface. This surface is in this direction. The vector, surface vector is in this direction. The electric field direction is this one. There is an angle theta between. So here in this vicinity, the small electric flux is equal to this much value. But if it is the surface is in this direction, so the surface vector and electric vector both are in same direction. So the flux here is maximum. This is the concept of flux. But the Gauss is a mathematician. He has suggested a very shortcut method to calculate this flux. What he is telling is, if any positive charge is there, you just imagine a closed surface. You keep it charge in the center, and around the charge, you imagine a surface. Then what happens? The electric field lines are coming out normally to the surface in all directions. So what is the flux? The electric field lines coming normally from a surface is electric flux here. So how to calculate the electric flux, total electric flux around this imaginary closed surface? He says that the flux linked with the closed surface is equal to the charge inside it. And see, here we have imagined this closed surface. Here there is no medium, there is no surface, there is no material, only air and vacuum is there. So this, from this vacuum only the electric lines are field lines are coming out, and from air, if air is there, it is coming through air. So the permittivity of air, here we have already discussed that electric field lines, when they are coming through, this medium has to allow it. So that property of a medium is called permittivity. So divided by the permittivity, here air and vacuum are there. So the permittivity is permittivity of free space. This is what the Gauss says. Gauss statement is the flux linked with a closed surface is equal to 1 by epsilon naught times charge enclosed in this closed surface. But before that, we got a formula here. While we are discussing about the basic concept of a flux, flux formula is actually the field, the dot product of scalar product of field and the scale, this what you call surface vector. So we can have a here the flux value given by Gauss theorem. So normally its formula is electric field dot product, the whatever the surface you have selected, that small surface vector, right? See, here is a how to calculate total flux is the point. If the surface is like this, open surface we call it as. Here all electric field lines are coming out, coming out, coming out. So this is the area. So number of electric field lines coming normally from a area gives flux. So this is open area. How to calculate the flux for the open area? This is nothing but integral, because so many lines are there. All this area we have to consider. So we are integrating. So integrating electric field dot product and the vector norm. This is the area. So area symbol we are normally using A or S. So yes, S bar. If the area is small, then A bar dot ds bar. Actually, this is the normal vector, normal to the surface, whatever we have selected. This is the thing. But here, see, the surface is a closed surface. Open surface, this is the formula. Here surface is closed. How to use? See, if the charge is there, if surface is closed, if electric field lines are coming out all in all directions, 360 directions, then we have to take surface integral. We have to take surface integral. Then at this particular case, we have to calculate the flux around the surface. Flux around the surface is equal to, here integration we have to take. This integration is around the whole surface we have to calculate. So surface integral E bar dot ds bar. This is the actual formula, but Gauss has given a shortcut formula. Whenever a charge is enclosed in a closed surface, the flux linked with this surface enclosed by charge Q is the charge divided by the permittivity of the medium. Here we have taken the air, so this is the permittivity of the medium. So here the Gauss law, we got surface integral E bar dot ds bar is equal to charge times charge divided by epsilon naught. So, my dear students, the Gauss law gives us the easiest way to calculate the flux linked with a closed surface. So, the surface area, the dot product of surface area and the electric field gives us the flux linked with the surface. So let us go forward. Now, see, let us go further discussion. So what we came to know is, if a charge is there, around the charge, we have, imagine a closed surface. So electric field lines are coming out normally in all directions. Electric flux is linked with the total surface. Total electric flux linked with the surface is equal to surface integral of E bar dot ds bar. This is nothing but the charge enclosed in this divided by the permittivity of the free space. Suppose, for example, let us consider a square. a cube, charge plus charge is exactly at the center. So in all directions, electric field lines are coming out, right? What is the total flux linked with this surface, this cube? This is one you may be asked in the exam like this. So what is the shape of this surface in which the charge is enclosed? A cube. How many surface are there? So total charge, total flux linked with this is, according to Gauss law, phi is equal to charge inside the cube is this one. This cube we have imagined, it is not made up of any material, so air is only there here. So epsilon naught, simple. But see, here also electric field lines are coming out from this surface, also coming out from this surface. So all total, how many surfaces are there? 1, 2, 3, 4, 5, and 6 surfaces are. From all 6 surfaces, the electric field lines are coming out totally, total cube. This is the flux around the cube. But each surface, each face. So each surface. How much flux is linked with surface? So we are having 6 surfaces. We are consider one surface among 6. This is the flux linked with each surface. If 2 surfaces we have to consider, then 2 surfaces among 6 we have to consider. If 3 surfaces among this one. If 4 surfaces, this is, if 5 surfaces, this is the flux linked with 5 faces. If all 6 we have considered, then the total electric flux linked with the cube is equal to charge inside the cube by the permittivity of the free space. So like this, we have to apply the Gauss law. So Gauss law says the electric flux linked with a closed surface is 1 by epsilon naught times the charge enclosed in the surface. So if the charge is exactly at the middle of the square, this is how we have to calculate each surface, 2 surfaces, 3 surfaces, total 6 surfaces are there. So one surface among 6 we have to select. So the flux linked with each surface of a cube is equal to q by 6 epsilon naught, like this. This is the correct answer. If suppose same cube I will consider, if our charge is at one of the surfaces, center of the surface. At this surface, the charge is there, positive charge. In this, it is not at the center, it is on this surface. But according to our Gauss law, the charge must always be enclosed in a closed surface. It should not be outside. Here, if you consider, suppose I will take one. If I consider a book here, the charge is at this surface. The charge is middle of this surface. So if charge is here, it is exposed outside. It should not be like this. So according to Gauss law, this charge should be enclosed in a surface. So what to do? I will imagine another surface, another cube here. Then what happens? Whatever the charge we have considered at this surface goes inside to this big rectangle. Then what is the flux linked with the total what you call surface? Let us calculate. See, what previously we know is, if electric field is in this direction and the surface vector is also in same direction, then flux is maximum. If electric field is in this direction and the surface vector is spreaded in this direction 90 degrees, then phi is equal to minimum, that is 0. Why? Because sin 90 is equal to 0. Sorry, cos 90 is equal to 0, right? That's why. Let us see here. See, if we consider positive charge here, the electric field line is coming out normally in this direction. And from here, the electric field line is coming normally in this direction. This is the surface. This surface is going outside like this. So for this surface, if you draw normal, the surface vector is also in this direction. Here, the surface is this one. It is also going out normally. So E bar and ds bar in same direction, right? Let us see this surface. Let us see this surface. See, electric field is this direction. See, electric field is in this direction. The surface of the surface vector direction is this direction. So electric field is in this direction, and the surface vector is in direction. So this is 90 degrees. So whenever 90 degrees is there, the electric flux is equal to 0. So this surface is equal to 0, this surface is equal to 0, this surface, all four surfaces are 0. So only these two surfaces are, but see one thing, don't confuse. See, if any charge is enclosed in a closed surface, the flux outside the surface is equal to whatever the charge inside by the permittivity. Here we just imagining the surfaces. So air is only there. So permittivity of the free space. Okay. But how many surfaces are there here with the maximum flux? Only two surfaces. On other surfaces, the flux value is equal to 0. So from each surface, what is the flux linked? Q by epsilon naught, only two surfaces. So we are considering one surface, comma 2. So if the charge is at center of a face of a cube, then total flux is equal to Q by epsilon naught only. But each surface, the flux is equal to Q by 2 epsilon naught. Like that, many problems they will ask in the examinations. If the same cube you take, if the charge is at one of the corners, see, the charge is exposed. It should not be like this. According to Gauss law, the charge should be inside. So we have to consider. So here, one cube I have to construct here, one cube, another one. So to cover this charge at a corner, I have to place here backside one cube and here one cube. Total 7 cubes I have to place. So total, how many cubes I need? Total, because one cube already there. So around this, to make this charge inside, so I have to construct 7 more cubes. So total, these many cubes I have to keep, so that this charge will be inside. I think you are understanding, and it is all related to geometry. So this one, see, for example, if this is the cube, this is the book is a cube. Here charge is there. Here charge is there. So to make it inside, I have to place here another book. Here also, and upside also I have to keep. So total